Thumbs up. All right. So yeah, okay. I have to kind of review a little bit what we did last time. All right, so last time we talked a little bit on section 46. We were finishing up that basically tuning our neural network and stuff. And you know that I kind of went into quite a lot of detail for like 45 and 46. And the reason why I think that's important is because essentially it's your building block for all other deep learning stuff. So if you have what's it called? Like if you do anything with neural networks or any deep learning stuff, it's kind of nice to know how these things work, how you can tune them, because everything after that, such as convolutional neural nets, we talked about last time a little bit, and then recurrent neural networks, sequence-to-sequence models, they're using deep learning. Those will inherit a lot of the abilities and kind of hyperparameters that you would use in neural networks. So hopefully that kind of gives you an idea of like what you can kind of do, and you have a better idea of like how you can tune things and optimize stuff. Okay, and so also last time we talked about where convolutional neural nets, we kind of talked about very briefly, and then I think yeah, we kind of like went through parts of section 47 essentially, like very quickly. I'm going to go in a little bit more detail today, and then we'll actually talk more about transfer learning as well. And I'll show you a few applications that actually combine a little bit of convolutional neural networks in transfer learning. And we'll talk about like where those are used. Okay. This is going to be a lot more kind of like open to questions time. Like if you've kind of gone through the sections and you're like, I wasn't sure about this part, or if I'm starting to talk about it, you're like, like I don't quite understand this part. It's like, oh, can you go into more detail maybe? This is a great one. I won't show as much code necessarily, but I can if you guys kind of like, if you're like, oh, how would you do this part? We can look it up together. Okay, so a lot more freeform than maybe the past couple sessions. Okay. So let me go ahead and share my screen, and I'll have to reorganize my windows again once I share my screen. But let's go there. Okay, and can you guys, I can't tell when it's full screen. Okay, good. I am sharing the right one. So sorry, I had to rearrange my windows. So many windows open. Oh, there you guys are. Okay. For some reason, Zoom puts the windows of all your guys' beautiful faces off to the side behind other windows, and I can't find you guys. But now I can see you all, and I can see you guys, your reactions and everything. Okay, so this is something I kind of talked about a little bit. I kind of mentioned very briefly that this was like an older version, and I realized I don't know what happened to my newer version, which makes me wonder if I got rid of it. The wonders of not using Git properly. Oh, well, it's all right. It's not like we're going to miss too much information, but we talked about what CNNs are good for. They're usually associated with like image recognition and like computer vision, but they're also really useful, like for example, finding patterns in speech. So actually like, using voice and stuff like that. And it turns out like convolutions in general are just really good at finding patterns that are bundled close together. So here's a couple, like I actually found a couple articles that kind of like, or maybe more research about how these can be used. So one is like text processing, which is usually not like, I think for most people, if you hear convolutional neural nets or CNNs, they don't think text or language, they usually think image, but this can actually work really well with language as well, because certain words that are grouped closer together might have patterns within them. So you can actually use convolution. So you can kind of see here, wait for the video and don't rent it. Those things have different groupings. So there's this great article here that kind of talked a little bit about using a CNN for text data and stuff like this, and seeing how it kind of works with making predictions and kind of going into NLP stuff. So know that CNNs are not limited to images. They're just classically talked about in images because they're the most like understandable, and they were kind of developed for images in general. The big reason why we're using CNNs over like multi-layer perceptrons, right? MLPs, are neural networks that we showed before. Last time we kind of showed a little bit of like how you would implement this with, I think it was like the fashion MNST, right? So like we tried that and we said like, oh, you could get something, I think that like 80, like the high 80s, maybe low 90s % accuracy on that. And it turns out that does, you can do neural networks pretty well. The big thing about that, the reason why it can do so well on those kind of images is because those images are essentially already like framed into a nice little spot, and like they're all about the same size. We don't have to worry about, if they're twisted or, if they're what's called upside down even and stuff like that. So this is the kind of stuff like works really well with neural networks. But if you want to do something more complicated, like a real life image, right? So pictures of like, here's a little quick example of these different house numbers, these street view numbers, this actually data set here, you can see is that, first of all of these numbers, they're numbers, probably as like, a literate, human being, we can see this and we're like, hey, like that's 2222, well, I'm gonna have a hard time seeing this one, but you can start seeing the numbers 104, 72, even though they're different colors, different shapes, different angles. Neural networks in their purest form, MLPs, just aren't gonna have a good job time doing this. And does anyone remember like how we have to actually take this two-dimensional data and feed it into a neural network? What did we have to do? Does anyone recall? Because we can't just simply give it an image. Mm-hmm.
Right, you have to unroll it into just one long vector, right?
Yeah, that's right. Yeah, you can kind of think of this as like a matrix of pixels, right? So like you can imagine this whole like row of pixels. And what we have to do, we, like Jenny said, unroll it. Usually we call it like flatten it. We take that matrix and we flatten it down. Essentially, we take that first row here, and then our second row here, and then our third row here. So the problem with this is that we lose a lot of spatial information. If the picture is always going to be centered around the single image, like the single number, it's pretty easy. But if we start having different variety, and then we can also have these different angles, like think of this 104 here, is that the first number is going to be on the bottom left corner. If we split it up like this, you're actually going to have this data here actually going to be very late in the neural network. So this is where convolution neural networks are really nice, because instead of taking data as, as a vector, we can actually take it as the full matrix itself. Essentially, we can feed it this picture. And what's nice is we can actually find these patterns, and we can even determine things like, or not determine, but we can even deal with parts that are rotation, different colors, different sizes, and stuff like that. So it's nice is that we can basically detect, it's like, oh, is there a number 1 in there? And it doesn't matter where the number 1 is. Okay. So, all right. I gave you a kind of quickly showing you like why we use convolutional neural networks. They're actually structured very similar to like multi-layer perceptrons, right? Is that basically we can use the same optimizers, we can use the same loss functions. They're also like a layered network. So you'll see here, basically we'll take the original input here and we'll actually create these like what they call convolutions. And what's really interesting is these convolutions, these filters, are really just like a specialized neural net for each one of these, like you can imagine these little pieces of paper. So like, I'm just gonna quickly show this because I think it's kind of a nice thing to kind of see. Is that if you remember our neural network, we have our inputs like this, and we would feed it into the next layer, right? Into the next neurons. Let's say there's like, I don't know, let's say there's 2 neurons here. I'll put 4. I know I'm crossing over the part, that's all right. So one thing that with convolution is that we can actually take a matrix of things. And so if you imagine this is like A and B, and this is C, and this is D. Instead of feeding every single part, we can kind of essentially feed it to say, okay, let's just feed it to these 2 ones, and these 2 ones will feed it to here. And what happens there, it keeps that structure together. So essentially we're not connecting all those neurons together, and we're kind of keeping this spatial information, kind of saying these things together are important. And then saying these 4 neurons will actually combine together into like the next layer, right? And so what's cool is that we can actually build up essentially, I like it to picture like each of these little like pieces of paper are kind of like essentially more sets of neurons. So like we would have a different set of weights that connect these kind of like parts of the image. And essentially that's what we're doing, is that each part of like these convolutions are essentially like a specialized little tiny neural network. And that's why we're able to use the same functions, optimizers, loss functions, and everything like that. So sometimes that kind of helps. Generally how I see it, and I think it actually does a very great job, but I think that's kind of a nice background. But like generally how you see this kind of implemented or showed is, let's see if I can find it real quick. I'm kind of jumping around a little bit, but that's okay. Here it is. Generally what you'll see is the picture, like the image down here is kind of like this 2-dimensional image. And then the top right here is the convolutional like layers. And essentially what happens, you can see like it's kind of moving across. This window that's in gray here is that window right there, you can think of like, those are all the neurons, the pixels that are connected to this one neuron here. And they all have different weights that connect together. And then we take all of these things and organize them into a nice 2D array. But you can just as easily kind of flatten it out and just know that only certain connections exist. But I think in general, this is kind of like, okay, this is kind of more or less easy to see. And you can see here is that a big part of our filter, which we'll talk about in parts, is that this window gets dragged across the image and it's being summarized into essentially just one number. And this one number is going to represent parts of, whatever that gray window is. And then we can drag across this part. So essentially what we get is kind of like a summarized information about the image based on whatever this particular window is doing, whatever this particular filter is doing. And we'll create this kind of different, what's it called? A different kind of summarization. Now what's cool is that we can actually build another one of these windows, right, with different kind of weights, with different kind of connections, and we can determine new things. And usually how we kind of see this, this is just one kind of filter. You can imagine that there would be actually like multiple filters. So there'd be kind of like a second filter here and a third filter. And we just basically drag a different kind of window with different weights and creating these different filters. So sometimes you'll see this as like multi-dimensional. So one picture of this kind of looks similar to this guy right here. So essentially what happens is that we're dragging different filters across and we create something like you can see here is a dimension here. If you imagine like going, I'm going to just draw it because good luck for me, like kind of motioning, is that this direction and this direction is generally smaller than the original dimension of the image. Okay, so if you imagine like resolution, right? Like if you have more pixels, right, you have a better resolution. You're essentially like making it fuzzier, but each of this information now has more information about some specific aspect of that image. And you can imagine like these are a stack of papers essentially, like this is a book of filters essentially. Okay, so we can imagine like the filters, this dimension gets larger and larger. So you'll notice that in general, convolutional neural networks, especially if it's kind of shown you this way, is that they'll tend to get smaller in the direction of like the X, Y. So they kind of like they lose resolution, but they'll get more like depth essentially. Essentially, there's more and more context information. Okay, so the idea here is that by the time we get to this very end here, before the fully connected network, is that we have so much context information about like what's in the image versus like where it is in the image. Like if you think about this, pixels are kind of essentially like the ultimate like, is it bright here or is it dark here in the image? And so that's really what the difference is between like an image here and a final like set of convolutional layers. Okay, everyone follow me? Okay, cool. And then finally at the last part, we basically take, this set of conceptual, like what's in the picture essentially, what's in the image, and we feed these features into a classical, neural network, which we usually call a fully connected neural network, sometimes represented FCNN, right? And the idea there, we just basically have new features now, and we just say, oh, based on these features, is it, whatever we're trying to classify it to be. Let's say a car, a truck, a van, a cow, a cat, a dog, a person, whatever you want it to be. Okay, cool. Any questions overall of like this view of convolutional neural networks and kind of like conceptually what's going on? Okay, and I think this is the important part because it's really easy to kind of just see the code and the math even sometimes and just be like, I don't know what's going on. Like I can do it, but like what's actually happening? And so it'll be nice to know like what's happening each part so we can actually say, okay, now we can build up our own convolution or see what other people have done with other convolutional neural network architectures and saying, okay, this is why this works really well. Okay, so, all right. So now that we kind of got a good idea of what this looks like, I'll close these guys so I don't reopen them again. Is we can talk about the different like actual layers. So I showed this like quick, GIF going through. I'm actually going to refer a lot to this kind of like this cheat sheet that's done from Stanford's like CS230 class, which is pretty available for you to kind of explore and stuff. But the main thing the big innovation is that window that's going to drag across. And so we can call this like little window and it's moving across and this will actually find different patterns and stuff. And this is what we call a filter. So this blue in here is that filter right here, essentially, or we're dragging this filter across and this will be summarized into some data point. And these are represented by colors, right? So essentially we have this for us. So there's a few things we can kind of adjust to filters. One essentially is just the size of that filter. How big is that filter going to be? You can see like in this case, it's a 3x3 kind of window being dragged across. It can be bigger, it can be smaller. Usually 3x3, 4x4, 5x5 is usually as big as you typically see. But feel free to play around with it, especially as you're first learning. And then the next part is something called stride and padding. And basically it describes how we move that filter across the image or, whatever like layer we're looking at. And so stride basically can tell us like, do we move it like skip over every part? Do we drag over every individual pixel? And then this padding here also tells us if we include all the information. So one thing you can see here is that when it reaches the end here, it kind of skips over. but it means that essentially like these layers in the middle here get seen like 3 times. You see like when it's the last layer, this middle layer, and then the first layer, right? But this like right layer here only gets seen once, essentially, just when it's at the end. So sometimes, depending on the application, what you can do is actually add this padding at the end here. And essentially that padding, like we call like zero padding, essentially allows it so it can go all the way to the end. So it sees this part of the image 3 times. So instead of ending, you saw like how it ended at the edge here, it would move on. So the filter would look something like, oops, get my little drawing tool. You can see it looks something like, be like this filter right here. And then these would all be a bunch of zeros on the side here. And then it would look something like this right here, and then a bunch of zeros on the side. And that way it sees those edges more than just that one time. So that could be useful in some cases, especially, basically it means that if you don't have this extra padding in here, it could potentially miss information, which might be fine for some applications. And other times, maybe it's really important to actually see that edge, those edge pixels. Okay, everyone understand that part? Okay, cool. So this is where like it's really tough for me to draw and everything like that. So I always like to just use what other people have already done because other people are amazing and I like using their stuff. So I'm going to again reference a lot what's going on here. I see a little thing in the chat. Is there no question? All right. So someone says, why does the dimension of filters always odd numbers like 3 by 3 or 5 by 5? So you're talking about more like the size of this filter, right? Yeah. So in general, it just tends to be something that works well. It doesn't have to be. It could be a 4 by 4. I've seen that been done. Typically, we might use a 3 by 3. That way, we can actually use that essentially. Like you'll tend to see odd numbers because then you can have the option of adding padding or not. If it's even, they tend to fit really well. And just those other size filters just means that you can turn on padding or not. That's what I think the general idea for using that. Okay, good question though. Okay, and so I'm going to point over to this guy right here, which is like this nice cheat sheet from Stanford. Basically goes through like all parts of like convolution, just a really quick like kind of overview kind of deal. And so the first part, like this is actually where that GIF comes from right here. You can see that window going over. There's the next part, which is called pooling, which we'll talk about in a second. But the first thing I want to talk about is this filter. So remember, I could say filters are kind of like essentially a stack of different things. So you can see here is our filter is like, let's say, a 3 by 3 or a 5 by 5, or, could be whatever. This case looks like a 5 by 5. And then the C here is saying how many different kind of filters we're dropping through. So what's kind of cool is that essentially we can say, here's the first filter, drag it across the image, and you basically have like a summarized image in that part. And then we say, okay, let's adjust the weights within this filter, and let's drag it across the image again, and you get this second layer right here. And you would do this for multiple times. So you might do this like, let's say 36 different filters or something like that, or like 50 filters or 100 filters. It could be very, very large, okay? And then what we can do from there, say, okay, like we can take this information and pass on to the next part. So that stride, like I mentioned, is basically saying how you're moving across the image. So if you're skipping like every other one, or if you're dragging over one, or going one, skip over one, skip over one. And so the idea there is basically you might, well, let me ask you guys, why would you think you might want to reduce, like make stride bigger? Because like by its nature, if you're moving across it faster, right, essentially skipping over parts, you're going to lose information. So why would we want to do that? Anyone got a guess? Sorry, I gave it a little silence, right? Make it a little awkward first. So, yeah. So first thing is that we would use a stride, right, to get all this information, right? You just think like, oh, we'd want all the information. Why would we ever use like a stride of 2 where we skip every other one, right? One of the things is that we want to make sure we can actually train the model, right? And so if we have too much information, making that stride bigger can be one thing. It's like, well, look, like, sure, we're skipping every other one, but we're still seeing most of the pixels, majority of the time. This will be fine, essentially. It'll reduce like the overall resolution, essentially. So if you had like a stride of 1 and you had like, went through every pixel, your filter will be the same size as the image. You can see it's like, well, that's fine, but now it's like we got to feed that image into the next layer, and we're going to have multiple copies of that same size. That's going to be a huge deal. It's like we're going to have like essentially more copies of that image, with slight variations and stuff. So the stride allows us, or can allow us, to essentially reduce that image size. Kind of similar is like the zero padding, or like, sorry, the padding that we can give. So there's usually zero or valid padding. Zero basically means that we just add our extra like zeros on the side. Valid basically allows us to keep like, it will just say, okay, like whatever you can put through here. So valid tends to be used to help reduce the size of that like next layer. So you can see here, for example, on this valid part, it's just skipping over the next part, right? And you can see here for full is that we have zero padding on every part. So now we should actually get the same sized image as before, if not actually a little bigger, depending how much padding you actually put in. Okay. Because remember, each of these parts, I shouldn't say, sorry, this should actually be the same size as the original image, because you're seeing, what's it called? This one window is being put into one number. So you should hopefully see the same size image. Okay, cool. All right, so this is the different parts for like the filters. Okay, and this is where I kind of go over to interactive example. Yeah. This is where I think, has everyone checked out this, I think I sent that as like homework, last time. If you guys, give me a thumbs up if you guys looked through it already. Cool, so I don't have to read through any parts of it, right? So big thing, kind of play around with it and stuff like this. The idea here is like, this is the actual image, right? So we start off with this image, you can see it actually in its native form, but it blown up here, you can actually see individual pixels, right? Which are all represented by those numbers. And then what we can do here is this filter, which is going to be this thing that we're going to drag across our window, right? And you can see like that little red dot on the far right here on the secondary image. You can see basically it looks like that image, but it's kind of like some features kind of enhanced, or kind of like some kind of summary essentially. And so we can do this by essentially having different weights. So whatever the number is in here for that top left part, you multiply by 0, -1, 0, -1, times 5, -1, 0, -1, 0. Note that this kernel is called sharpen, which kind of makes sense. It's basically emphasizing the middle pixel. It's like whatever that middle pixel is, emphasize that a lot. And so you can kind of see basically that's exactly what's happening here. That's why it's called sharpen. You can see that these features are basically being really enhanced that are kind of in the middle. But we can also change these weights. So if I change it to a different one, say to like, let's say right circle, you can see here is that the numbers change here. And you can see in this case, it really cares about on the right side here. So if you move off to the right here, you can start seeing a little bit of like what gets really emphasized. So you can see here, this area, if you look on the, I wish I could like point right now so you could see, but on the right image, you can see as I move this filter up and down, most of those are dark because basically that's where the edge is. And you can see in this case, when there's not really much over here, you can see it's all mostly white, because basically this left side of this little filter is being basically zeroed out, or like even negative, right? And so the point of this one is actually finding those right edges. So that's kind of the idea here, is that it's actually finding the different edges of where things belong, okay? So you can start playing around with a whole bunch of these things and see different ways filters. So you can imagine each of these different kernels, right? These different like set of filters with different weights, essentially a stack of different like summary of these images right here. And note that these are, I think it looks like it's the same sized image as before. So because we can do zero padding. So notice that if I go all the way up to top right here, I can actually drag across and you get numbers, versus if I go all the way down here too, you can see I get numbers, okay? So again, you can start seeing this applied really well when we put it to a specific image. For example, if I change something like, let's say outline. So you can see the outline is really emphasized from that original image. I don't know what the original one, I don't think I can do identity. So identity is, this is the original image right here. So you can see here basically just whatever's in the middle here. And then if I added, for example, let's say just this is going to be 1. I don't know if you guys tried this out yourself when you're playing around with it. You can actually start looking for things for like diagonals and stuff like this. So what will happen is that this will tend to actually only look for things that are at a diagonal kind of set. You can do things like saying, just look for the middle one here. And so if you start looking at that, it's like, okay, like that means when I look at, for example, outline, you can see here basically the middle parts are right here turning into black, and this center part is basically being darkened a whole lot, right? Or I should say emphasize a whole lot. Okay, so this is how you can use kernels to basically get new information, new ways to view the same image and summarize it. Okay. All right. Any questions on this filter and all that stuff? Everyone feel pretty comfortable like understanding like, you can adjust those weights, Cool, awesome. And remember, it doesn't have to be a 3x3. It can be other size filters. In general, 2x2 would be like the smallest one you tend to see. There are cases where you actually would use a filter that has literally just like a size 1x1. But those are like different kind of applications and stuff like that. So in general, you'll see things like 3x3, 4x4, or 5x5. Okay, cool. All right, so let's talk about the next part, which is pooling layers. So in pooling layers, we have two main ones that we mostly talk about are max pooling and average pooling. So one way we can kind of think of pooling layers is, again, to kind of like downsample the size of the image. Essentially, we're trying to get less resolution, essentially. And the idea there is that there's going to be a lot of redundant information right next to each other. So the idea is like if you have a little filter around something, there's probably not too much more information in that very small area. So we can use pooling to basically say, okay, let's just take the maximum or just take the average of that. So again, this cheat sheet right here has a pretty good demonstration. So you can kind of think of it like almost like another filter. And you can see here as it's kind of getting dragged across the side here, it's actually taking the maximum in this case, and it's recording that information. And the average here would do basically take whatever's in that filter, right? And say, okay, like pull it together to be some kind of average. Okay, so yeah, and the main idea here is that you're just trying to summarize more information. We're getting less and less spatial information and more contextual information overall. Okay, so again, this kind of fits well with our kind of idea of like reducing its size essentially. Okay, so you can see going from like this convolution layer and then going to pooling, you can see this pooling is going to reduce that size, right? Because imagine if you have a 2x2 and you only get the one number in there, it's going to reduce it in half in each size. Okay, cool. All right, and those typically will go between convolution layers. And then our last one is our fully connected layer, which is just basically at the very end here, we have our kind of set of complex contextual information, and we feed that contextual information essentially into this fully connected layer or neural network. And this is the thing that actually does the classification of what's going on. There are CNNs that are called fully connected convolutional neural networks, which essentially instead of having this neural network in here, I'm sorry, I said fully connected, fully convolutional neural networks. And basically instead of the end here is an actual convolutional neural net. And the idea for that one that you can actually use that to see where the activations are and stuff like this, and that can be used for location, like image location. So not so much about classification, but saying where does the image really pop up a lot. So you can think of like, you know, for example, if it's classifying something as a dog, where's the dog in the image? And at the end here, it just tells you it's a dog. It doesn't tell you where the dog is. So that's where sometimes fully convolutional neural nets can be really useful. It can tell you where that dog exists or where that image is classifying. Okay. All right. Any overall questions about anything we talked about? Okay, sound pretty good? Thumbs up sometime? Okay, see some nods, cool. All right, one thing I did want to note that kind of skipped over is you'll notice it's convolutional pooling, convolutional pooling. The reason why we have convolution is we're trying to basically patterns within patterns. So you can have convolutional neural networks go very, very deep and basically find patterns within patterns within patterns within patterns, which again, kind of like what we saw with neural networks, where neural networks having like, you know, essentially the simple stuff and then going deeper and deeper and deeper in finds more and more complex patterns. Same idea here with this convolutional neural net. Okay, cool. So that leads us to the last part of like this section 47, which is like visualizing convolutional neural nets. So the reason why you might want to visualize a convolutional neural net and see the different layers is just to see what is it doing. You know, the neural network itself is not going to tell you, like a random forest is going to tell you where it made its decision. This is going to be basically trained, like the weights for all of the CNNs are basically just going to be trained as we give it more and more examples and go through different epochs and do backpropagation and everything like that. So at the end, it might be useful to say, hey, what are you doing? So this, for example, I pulled this from a blog from Karis here, I think. I'm not going to go through the code for this. I think the curriculum actually shows a whole bunch of like how to do this kind of stuff. And plus there's a lot of resources for you to see. But the one thing I want to note here is that you can see this is the first convolution layer of the first filter. You can see that it's like they're relatively simple patterns, right? You can see like some dots, maybe some wavy lines, some looks like almost like little speckles, right? Some almost like static right here. So it's detecting those kind of patterns. And then as we go deeper to the second convolutional layer, the third convolutional layer, the fourth convolutional layer, we get into more and more complex like parts of like detection, stuff like this. And essentially it means that these things right here, what this is visualizing is saying, if patterns like this exist, this particular filter is going to like go like, hey, this is super important. Like you should like, you know, these are going to be high values essentially, versus this filter, if they see really curvy lines over here, it's going to like say, hey, that's really important and stuff like this. And you can see as we get deeper and deeper, you can start getting really complex images and stuff like this. In fact, there's some things that you can actually find in certain convolutions for like that are trained for multi-class and stuff like this. You can actually find things that are like eyes and like fur and like actual like building structures essentially, which is kind of interesting. It basically, the convolution is saying like, this is my ideal version of what an eye looks like based on my training. And so that's like what I'm going to say is an eye if it looks really close to this kind of thing, which is kind of cool. Again, there's this blog here from Keras, which I can let you guys go through. You can definitely see that basically what they're doing here is they have a model. You can basically have your own model, but in this case, they use a model that's already been trained. And then they basically take those different layers and you can start visualizing each part. And essentially what you're doing here, essentially you feed a bunch of static and say, here's a bunch of static. And you tell it to basically modify that image essentially to emphasize what it would do to maximize the values in there. And that's what you're seeing here. So it's kind of like working in reverse. So instead of saying, hey, here's the filter and apply it on an image and say, what's the value of this? You do the opposite and say, hey, filter, go ahead and modify this image to maximize what you would like to see. Okay, so that's kind of a cool thing to, again, check out. This is where you can see some applications. One, for example, is Deep Dream. Have you guys all heard of Deep Dream before? Give me a thumbs up if you guys have or not. Oh, you guys are in for a treat if you haven't seen this yet. Okay, so this is a little video here. I won't play through or anything like this, but I kind of want to show you a couple of things that you can do. So let's see if I can pull it up. Here you go. So you can see here is a picture. I'm trying to find it real quick. He probably has it a little bit further up here. So he takes the original picture like this guy. You can see this picture. So this is normal, like just painting, I think. I don't think it's real life, right? It's just got painting still. And you can see here, basically, it's like, oh, there's some trees, some leaves and stuff like this. And then he says, okay, and Deep Dream was developed by Google. It's basically their image recognition neural network. And they say, okay, neural network, go ahead and tell me, you know, like whatever you see, you know, if it looks like something, it asks for like one filter, say, whatever you see, go ahead and emphasize and change the picture to make that value even larger. And so what happens, for example, he feeds it in a filter. Let's see if it can pull it up now. You can see here, I don't know how well you guys can see that right now, but you can kind of see with like kind of buildings and like little animals kind of hanging out right here. And basically what it's doing is optimizing, saying, well, this kind of looks like some whiskers, or this kind of looks like a building. So it's going to modify that picture to make it look like a building. And this can actually help you kind of determine like what do convolutional neural networks tend to look at. This is after like, I think he talks about like so many iterations. You can basically make it iterate. Oh, good, there's a close up, I think. There you go. You can see some weird looking shapes and stuff like this. So this is where like, I think it's really funny that they call it Deep Dream, because it's kind of like, what do convolutional neural networks dream of? And essentially there's some really interesting pictures. Just know that like, probably don't do this before you go to sleep. It's a little kind of like, kind of creepy looking. But basically the idea here is that it saw something that kind of looked like maybe an animal, right? And so then it was modified on one iteration. Okay, modify it to make it more like an animal for what you think it looks like, right? And basically it keeps doing that over and over and over again until basically you'll tend to see, like, for example, there's a bunch of eyes. But you can also see here, this tends to look like kind of like a building. There wasn't a building there before, but something that looked like a building to that filter. It's like, hey, this kind of looks like a building. Go ahead and emphasize those features. So I think he has another one here. A great video if you haven't seen, if you'd like to see it. So this is the original picture. And you can see here now, it's modified the picture a whole lot. And you can actually see, for example, this building, which I think is super interesting. This is a kind of idea. It's like, we're like looking in the clouds. It's like, what do you see, right? Well, we're used to finding patterns and you can kind of imagine what those patterns look like. And they'll say, oh, it looks like a building, or it looks like, you know, a little cow or something like that. And in here, you can say basically the Deep Dream, right? It's kind of like, it's imagining this, oh, well, this activates my filter very high in this direction, and basically keep emphasizing that part. And basically you start getting these like really structural buildings. Like you can see there's very similar patterns. And for example, you can probably see some cars here, some wheels. You get some, again, really kind of trippy looking things. But honestly, this is a lot more fun just to kind of play around with, but it can also be used to kind of like help you emphasizing like, what is this neural network emphasizing? What is the thing that it really cares about? So anyway, great video, kind of watch through and stuff like that, kind of talk through. There's actually, I think he has it linked in here. If you look at, I think if you just look up Deep Dream, you can actually use, you can upload your own photos in there and basically have it, you know, do it. This is maybe like 2015-ish, maybe 2016. I can't remember the exact date, but when they announced this. So I'll kind of look up real quick, Deep Dream. There's one that I know in particular. It's like, they literally just took a picture of clouds, which I think is just kind of funny just to think. It's like, oh, what do you see in the clouds? So they took clouds, for example, and see like what kind of things you have, like what the kind of things they saw. So like this, for example, oh, this is a good one. This one right here is basically, this was used to basically on Starry Night, and you can start seeing where it find those patterns, and you can see, for example, all these different things. There's also some weird ones, like if I just do Deep Dream, but if I just do Deep Dream, there we go. So this is when we start getting some really weird stuff. For example, certain filters just love eyes for some reason. It's just like, oh, that's like the thing. And this is probably the one that people like to use a lot because there's this eyes just kind of just appear out of nowhere and stuff like this. Really kind of trippy stuff. But anyway, one application to show you like, you know, how you can visualize what the neural network's doing. And this, but to be quite honest, this is more for fun, but gives you the idea of like how you're doing visualization, visualizing what this neural network is looking at and stuff like this. One interesting one, I don't have a link to this research, but there's a researcher that was kind of looking at a research group that was looking at a neural network, and or a convolutional neural network, and they found basically, you know, they gave it like what is strength, right? So like they trained it like strength, and then they basically did the same process, like emphasize the image of static to give me something. And what they found, it made pictures. Does anyone got to guess what the pictures were? How would you say like pictures of strength and like based on image? Like that'd be a really tough one to say, right? It turned out it produced a whole bunch of like more masculine arms with like weights, but it was more focused on the arm itself than the actual weight. So you can start seeing things like, you know, how is it actually classifying? So this is actually really useful. For example, if you give a bunch of data that is biased in some way, and I say biased meaning that like there's not a good representative of like what you actually want it to learn. For example, if you want to, all right, so I might go on a little bit of tangent, but maybe this will be useful overall in convolutional networks. There's a story of, I don't know if it's really true, but supposedly like the Russians, like in World War II, or I can't remember what it was, but let's just pretend it's like some war against the Russians. They trained their dogs and to basically carry like bombs on their back, and they would go underneath tanks. And then the idea there is that they could basically take out a tank by, you know, exploding the bomb, you know, poor dog, you know, too bad. But they would train these dogs, right? And they would do it, and they would do it so well, you know, and, you know, with Russian and stuff like that. When they put them out in the field to try this out, instead of blowing up the tanks on the American side, like the US, like, you know, or not American, but like, you know, Western side, they ended up blowing up the Russian tanks instead. And the reason why is because all the tanks that they were training it on ran diesel. And so the idea, again, I don't know if the story is true, but kind of gives it emphasis, is that they trained it on diesel. And so the dogs thought, well, the tanks I'm supposed to go underneath are all these diesel, like that's where I'm supposed to go, is just wherever it smells like diesel. And that's where they would go to. So the idea there is like, you want to be careful with like, you know, what kind of training information you give. If you train something where identifying if someone's a guy or a girl, right, or something like that, and it just happens to be a guy's always wearing like a blue cap, well, then it's just going to start learning the blue cap means, hey, that means that's a guy. And now suddenly you don't have the right, what's it called? Like you don't have the right training set. Your training set is biased in some way. Okay, so anyway, this can help you identify those parts. Yeah, so sorry, a little tangent, but I think it's kind of important to kind of talk about. I'm trying to think what else. Oh, if you guys want to play around with this, someone built a kind of like a you take your model and you load your model in here. And basically in real time, you can then take a picture and you can see this, like you can select different filters and you can see our different layers and you can see the filters on what was maximized essentially. So again, another kind of cool looking tool that you can use to essentially like determine how well your convolutional network goes. And again, you can get some kind of fun art stuff too in there. All right, yeah. So I'm trying to think of anything I want to put out. A couple other things, video demo of, oh, this is a fully convolutional neural net, is that instead what you do is you add in a convolution, this is not done, talked about in the curriculum, but you add a convolutional neural network at the end instead of fully connected, and you can actually put in, it's called a gap layer. And essentially what you can do then is you can start looking at where the neural network actually like is maximized. So for example, this, I think this repo was trained on dog breeds. And so saying just like what the dog breed was, you can also show where it is really visualizing what makes this dog breed a dog breed. So this can also be really useful for one, detecting where it is in the image, but two, you can also determine like if you are training it on something that's like not what it's supposed to be. For example, like that training or strength example, where maybe you want strength to be represented by something else, but it's focusing on, you know, a blue cap or something like that. You can start saying, hey, like this neural network is not training, it's not learning on what we think it's learning on. So again, other ways you can kind of explore it, because these things act like black boxes where you put input in, you get output out, but you don't really know exactly why it made that decision. Okay. Yeah, you can see here kind of a quick visual demo where you can see what it's classifying it as and where the image is being detected. So yeah, cool. All right. Any questions on that part? Okay. And then the last thing, adversarial networks. Has anyone heard of adversarial networks? GANs, for example, generative adversarial. I see some nods. So this is actually really interesting. This is kind of like an adversarial attack was talked about first in research of saying like, you know, how you can trick a neural network. And then an adversarial, generative adversarial neural network uses that idea to try to emphasize like one thing over. So basically it's trying to figure out a way to, what's it called? Like trick the other network. But anyway, adversarial networks are attacks on neural networks are really interesting. So for example, this right here with their thing that they trained to be like detect, you know, if it's going to be a panda or if it's some other animal, it had about 57% confidence that it was a panda with the original model, right? Then what they did, they took this image and they added some static, which this is the image right here with static. And you can tell there's like, I can't see any difference. Like you can try looking at this, but there's like so subtly you can't tell any difference. So they add this little extra static essentially into this picture. And then running the model, not changing anything else with the model, it determined it was a gibbon, which is like a type of monkey. I sorry, primate, but a type of primate. And basically it determined that with 99% accuracy, where essentially it's like it completely changes what it determined. It basically, with this extra fuzz, it can actually say, oh, I'm more confident that's a gibbon than the actual true label, a panda, which only had 57%. So these are some really interesting things that kind of show convolutional neural networks. I think there's anything I else want to show you down here. No, I don't think so. All right, but basically showing you convolutional neural networks, like where they might fail and stuff like this. And this is important when you do your, do something for a thing or for like, a business. You want to make sure what you're providing is actually going to be, how can it fail essentially. One of the things you guys might have seen is something like you can take like a little sticker that they designed and they put on top of a stop sign, and then all of a sudden the neural networks that we're using for self-driving cars couldn't see that it was a stop sign anymore by just having a sticker. So yeah, so things that you kind of be aware of when you are training, stuff like that. This is not going to come out anyway. All right, so that's overall visualizing neural networks and like what use cases there are. Are there any questions about this, Chance? No? Okay, so I'm gonna go into transfer learning. And let me go ahead and just pull up that notebook. And this should actually be pretty good. Tell you what, I have about 12 minutes. It should be fine. But if I go a little bit over, are we okay if we go over by like a few minutes? All right, thumbs up. Okay, cool. All right, so I just want to put that in there in case we need to make it a little bit longer, because I like to talk sometimes. It's a really interesting topics. So, all right, so transfer learning. So there we go. So the first thing is basically is that convolutional neural networks and neural networks in general, they take time, right? Like you can imagine just trying to get this to work. First of all, getting the right parameters, right? Just getting those set, but also just like having time to train them. They can take hours at a time. On extreme ends, they can take literally days or even weeks to like train. So you can imagine like this can be a lot of work trying to go through. This neural network, right, or this convolutional neural net right here is relatively small, 1, 2, 3, 4, 3 or 4 layers deep, basically, of convolutions than a neural network here. But if you want something really complex, you're going to have more layers. In fact, if I look at ResNet 50, which was a neural architecture, this right here, if you look at it closely here, this was the architecture that was used for ResNet 50 that basically had, and each of these, like say convolution, that's each a convolution. So this guy right here, you ain't training this on your computer, like your own little laptop. It's just not going to work. So this was trained over weeks and weeks and weeks. So you're like, but it was really great because it basically was classification over like, I think 1,000 different kind of classes for images and stuff like that. So it was really impressive and useful. If you want to do that yourself, you might find that's going to take a long time for you to train. So transfer learning basically allows you to say, hey, someone already made this model, or even you made this own model yourself. What if I take that model and basically just adjust it a little bit so it fits towards my needs itself? And that's the idea of transfer learning. Essentially, you have a pre-trained model, a model that's already shown great accuracy and everything like that, and using it for maybe a slightly unrelated unrelated data set. So one example of this, there was a research paper about talking about detecting different types of skin cancer. And they basically used transfer learning, and they were saying, is the skin cancer, malignant or not, right? Is it benign? And the original model that they used was used basically to detect different farm animals and different animals and say, is a cow, is a dog, is a cat? And they used basically that model to help basically boost along detecting skin cancer. And so what's nice is that the reason why this works really well is because these early layers here, and to begin with, usually are used to determine like very basic patterns. But those basic patterns can be used for a lot of different things. So the idea here is that you could potentially use, the already structure that's already pre-built and trained, that's already like really good at detecting things, use those parts of the layers to basically determine other things, and then use at the very end your own classification, like maybe your own neural network here. So there's a few cases where this kind of depends on the similarity. The curriculum kind of mentions it, but I think this is kind of a nice kind of breakdown of like flowchart of like how you might approach this system. So one case, for example, is like if you have a model that's trained and your data is very similar to that, you probably don't have to do very much like modification, essentially. Like imagine if you were detecting things like you were doing dog breeds or something like this, like let's say the 20 most popular dog breeds, and then you want to try it like the 20 most popular dog breeds in, I don't know, Russia or whatever, like different dog breeds and whatever. They're similar enough that you probably don't have to modify it too much. Versus like saying you have something that trains against animals, but you want to detect skin cancer. That's going to be very different from each other. So these are the different situations, okay? So you have a large data set. So you have a huge amount of data, and you have similar data from the original model. Then all you got to do essentially is you just retrain the weights by feeding in the data. But the important part is you take the weights, instead of initializing them randomly, what you do is you start off with whatever weights you had to begin with and say, okay, now we're going to train the model from that starting off point with this input, similar data, and this output. So the fact that you have a large data set probably means you can probably do a decent job training it. And since you already have it very similar to the original data set, it probably means the weights are going to be already pretty close to where they should be, okay? And then at the end here, you just have a new fully connected neural network, because essentially that neural network is going to take new, what's it called? Kind of like these features, these conceptual features, right? And feed it through and do detection. So you'd have a new neural network with new randomized weights, because basically this neural network was optimized for that specific task, okay? So really the biggest train here is going to be just training the neural network to update these weights. But this one right here, you can basically just have it go through and it would basically learn the same thing. You probably, to be honest, in practice, for some cases, you might not even need to train this part. You could probably freeze this layer and say, don't train this convolutional part, just train the neural network. Okay, does that make sense to people, the concept? Okay, so then the opposite, the similar one, we have large data set, but different kind of data. So it's different from the original one. So in this case, if you want to have a good thing right here, since you have a huge amount of data, you could probably can train this network. So essentially you have already the layers from like low to high features, right? Saying like what's the most complex to like the least complex. And you say, okay, go ahead and randomize the weights. Since basically this different data is not gonna be good enough for you anymore. But you can at least have the same structure that you know works really well. Randomize these weights, retrain the weights, and then a new fully connected layer like before. And the idea here is that we have a large enough data set that we should be able to train this neural network pretty well, right? So the idea here is that like if it's not too different, you don't have to train you don't really have to train too much on the convolution. But if it's a very large data set and it's very different, you can probably afford the sense to train that part, and at least you'll get a better accuracy. This will take time, right? This middle part might take a long time, but you'll get more accurate results. Okay, cool so far? All right, so this is what happens. Transfer learning is super powerful when you don't have a large data set. So like if imagine instead of having, you know, like 1 million data points, you have like 15,000. It's like, well, 15,000 is not going to do very well with a neural network. So one thing you can do is that if you have a very similar data set and you have but it's very small, you can essentially just go ahead and freeze the weights right here. And the reason why we do that is basically to prevent it to overfit. If it doesn't have many examples for it to train on, it might try to think that it's really, it might start like optimizing for a very few number of examples, and it's not going to generalize very well. So the idea there is we can freeze it since it's very similar to it before, and then we can go ahead and train it again on just the neural network at the end. Okay. And then the last one, which is a small data set and different data. This is probably going to be like the hardest part, essentially, where you have not too much data, but it's also not the same thing as before. The idea here is that we basically remove the end of like the pre-trained layers and then freeze those weights. So the idea here is that we would actually remove kind of like the end of like this part right here and then retrained this part at the end. So the idea here is that you will still have all of this information that's getting like the basic features, and the very last layer here, which is going to be more complex features, or maybe the last 2 layers, those are the ones that you're going to say, okay, let me go ahead and train this guy right here. And that way, hopefully, you can get most of the way through and not worry about, what's it called? Like not worry about overfitting, but still get something that's beneficial towards your smaller data set. And then of course you have your own new neural network and everything like that. Okay, does that make sense to everyone? Okay, cool. Any questions at all? All right. One last thing you can do for transfer learning that can be really useful too is you can do something what I like to call bottleneck features, which are essentially you feed in your data set, like your original image right here, and you feed it through here and you stop it right here. And so the idea here is that this last layer is going to give you a matrix essentially, or you can think of it like a vector of different like conceptual features. And you can take these conceptual features and then train off of these. So what's cool is that this usually, if you freeze these weights and you don't train it, you just push it through essentially. You save these like matrices of like whatever this original image is, image of like some person over here, right? This is going to be a bunch of numbers right here. And you can then take these features right here and train off of this. So this is a really nice way to essentially saying, hey, we don't need to like have this whole neural network. We can just keep these features. And this tends to be very, very quick. So this can be something where like if you have like you need a really fast application, you can essentially have it pass through this ahead of time and then train it off of these guys. This is very similar to using the small data, but different data. Okay. So anyway, sometimes this might be really useful by itself. Okay. And I would say overall is that if you're doing something like for the neural network, it's a good idea to try out using a transfer learning technique, because it just tends to do just so well. It's kind of like one of the things that like, why not try it? Because basically someone else has already built this repo for you. So one last thing. So, okay. All right, we have a minute and a half left, and then we'll see if we have a time for, I'll show you really quickly style transfer. But I'll go ahead and show you this repo I had and just kind of show you a little bit like how this transfer learning can differ. This is one of my personal repos that I had done. So this is American Sign Language. Is anyone familiar with American Sign Language by chance? Not so much? Okay, so American Sign Language uses these things called hand shapes, which are like, you know, this is an A, this is a B, this is a C, a D, and stuff like that, and through the whole alphabet. There are 25 signs that basically don't rely on movement. So the only ones that do rely on movement are the letters J, because you have to move your hand like this, and Z, because you're going like this. So A, B, C, D, E, F, you know, going through. This paper that I did, or a little project, I should say, I did, basically took images of people's hands and said, okay, can I detect, you know, if this person, you know, if this is an A, it's a B, a C, or a D. And kind of showing you a little bit what this looks like while this loads is, I'll show you, I don't have it run. Why don't I have it run? Ooh. Oh, well, okay. I was going to show you guys really quickly. Maybe this will be quicker. Okay, so there you go. So like, these are different images going through. So what's interesting, there's certain like ways you can like say, okay, this is my project. I had to first pre-process these images over to a certain size, right? That wasn't going to lose too much resolution, and that'll be consistent all the way through. And then I would feed this into the neural network, convolutional neural network. And what's kind of cool is then you can then say, you can go up to an evaluation like a convolutional neural net, or not, sorry, a confusion matrix. And you can see here, this is my confusion matrix here. And basically everything on the diagonal means it's good to go. But you'll see there's little islands of like incorrect spots. And what's interesting is that this is how you can use like a confusion matrix with whatever you determine and stuff like this to see, you know, where you need to make improvements. So for example, on here is the letter, looks like T. So this is the letter T, but it was misclassified as the letter, or sorry, this was the letter A, and it was misclassified as the letter T here. And so this is an A, this is a T. So you can kind of see very quickly, like, oh, that makes a lot of sense. So this is where you can use these evaluations to really determine how well your model is doing. The way this happened too, and I was trying to pull this up, but I think it's not going to work here because I didn't have it run through. But basically, I tried at first using a really basic model of like a CNN, right? And you're like, okay, I got like 50%. When I tried using more complex models like VG16, and then later on I used ResNet 50, I ended up getting something like 70%, which at the time for the paper where this data came from originally, it was getting something like 30, 40% with just images. But with depth information, it was also getting like 70%. But basically saying, oh, if you get rid of depth and just use images and using ResNet 50, which ran really quickly, you can see here using kind of like getting these bottleneck features, it was performed really well. And this is the kind of thing you can kind of think about saying, okay, like we can use other models essentially to help enhance. So anyway, I wanted to point this out because this was kind of related to like how to do convolutional neural nets. But this is kind of like how you would see this whole, like you can see how there's a lot of work essentially going through pre-processing the data, feeding that data through here, loading that data set, and then what's it called, preparing your models and actually taking those models, and then finally being able to evaluate your models and seeing, you know, where it performs well and where it doesn't perform well. So you can see here, this is ResNet 50, and I have another, this is VG16. So you can see how they slightly perform differently from each other. Okay. So anyway, that is what I want to show you for transfer learning. All right. Cool. So that is all I had for transfer learning. I do technically have a part for style transfer. Would you guys like me to go over right now? Maybe I can go through it like maybe 5 minutes, or you can cut it here if you guys can get thumbs up if we keep going. Thumbs down, you gotta go. All right, see thumbs up. Okay, Lawrence has no. Tell you what, Lauren, this will be recorded too.
Sounds good. Sorry, yeah, I have to head to something.
No problem.
But I can look at the recording.
Yeah, I'll record. It'll be on the recording, so then you can definitely check it out.
Okay.
Cool. All right, no problem. And then Amala says, I always wanted to know what the transferred learning are trained on. Do you have any documentation? Oh, so like saying the original model of what it was trained on. Yeah, they're definitely, if you look up the papers, for example, I won't pull it up right now, but if you actually research, say, ResNet 50 original paper and pull that up, you can actually find the original data. Usually, I think it was ImageNet's, it was a competition. So it's like a set of data that you can train on. So I think it's like ImageNet. I don't remember how big it is, but you can actually get the original data from ImageNet. I have to do some research to find that directly, but yeah. Is that what you're talking about?
Yeah.
I saw in the chat. Okay, cool. Yeah, so what's nice is that a lot of times the papers will actually say what source they use because they're using some collection of data, like some data set that maybe it's in a competition or something like that, or available for everyone so they can all compete and try to get better results. So
Okay.
Yeah. For the record though, probably not, I think ResNet 50 ran over like 3 weeks to fully train on that data. It could have been longer, but yeah, just be aware. Like if you try doing it yourself, don't expect really amazing results from scratch. Okay, so let me go ahead. I'm gonna move this guy over here. And okay, I'm gonna move this guy here. Oh, of course you can. Okay, so style transfer. So this is gonna mix between convolutional neural networks and transfer learning. So there's this really great paper on kind of like doing this thing called style transfer. There's actually an implementation in Keras, which is basically what this code is going to be down here. But the idea here in this original paper is that you can take parts of the convolutional neural network and basically use one image as kind of like your template and your other image essentially of saying like your canvas. And so the idea here is that you can take parts of your neural network. You can see here basically saying what things are emphasized from this image and apply them directly onto a new image. So you can see here, this is your the target image here. And they applied different artist renderings, basically, what are the things that are emphasized a lot. So it's kind of cool, it gives a lot of like kind of like extra like artistic, you know, kind of play around with stuff. But you can also see like what layers, you can choose which layers you want to do and see where those complex parts go through. What's also cool is that you kind of get the feeling essentially, or like the essence of like what this picture is on top of another image. So for example, I have like this is a famous example. We take Mona Lisa, you combine it with Starry Night, and basically you get a picture that's relatively close to that kind of like style essentially. So what's cool is that you can actually run this code. So I'll just kind of quickly show you guys what this looks like. The big part basically is going to be loading this image. And then from there, we say, okay, we have our actual neural network, which I think it defines it. Yeah, we're using VG19. So note that Keras basically has these pre-trained neural networks, convolutional neural networks in their package. So you can actually load them directly with all their weights and everything. So since I already know what the structure of like a convolutional, this VG19, basically I'm just preemptively putting this together. And then what you can do essentially is you can say, all right, how much weight should I put on these different layers? So you can say, okay, for this block 1, block 2, block 3, block 4, block 5, I can say how much emphasis should you put on using those, what's it called? Those layers onto the target image. So what's going to happen here in this actual image style transfer is essentially what's going to do. It's going to basically calculate this kind of like saying, how close are you in style from this, like, let's say this image, how close are you in style to this artist rendering, and how close are you to the actual content of this image. So it's really cool. You can actually combine basically saying, all right, neural network, instead of optimizing for a loss function of saying, are you classified correctly? You can actually say optimize for saying this specific new loss metric, essentially saying how much style you have and how much content you have. In the end, basically, it's going to try to balance between those two parts. So if you add too much style, I think the paper kind of shows this. If you add too much style, you end up getting just basically just the picture, the original picture, more or less, right? But as we reduce the style and put more emphasis on the content, you can actually get these kind of parts where you get a mix between style and content together. Okay. So I just thought this would be a kind of cool thing that you can play around with. And I just show you an example. As I ran this earlier, because it takes like, 10 minutes sometimes, use a GPU on this guy. This is the same exact code, and I just printed it out at the very end here. You can see here in this case, this is the first like 5 iterations that go through each part, and it's trying to optimize of saying, keep the style of a, in this case, Starry Night, and then, but keeping the content of Mona Lisa. So in this case, you can see I only did it like about 20 iterations. So not a huge amount, but you can kind of see how you can kind of make new, first of all, new loss functions to create new functionality using a, what's it called? Transfer learning, basically a pre-trained neural network. And then finally actually saying, well, how do convolutional neural networks actually work? Like what are they actually saying? So I think it was a kind of a cool little project that you can kind of check out. There's a whole bunch of now, like I think like repos now out there for style transfer. Again, Keras has this implementation right here, though this is meant more using Python. So you can see this is how you would feed it in. I just kind of repackaged it up into a notebook that you guys are probably more familiar with. Okay, so this is also in the repo for deep learning convolutional neural networks. All right, but that is it. Yeah. Any overall questions before I end it here? I see a little chat message. So what advice can you give to determine the number of layers to unfreeze? Ah, yes. So in general, you want to know first for transfer learning, is that like what set are you in a large data set? Are you a small data set? Or are you similar data or different data? If you are different data and small data, you tend to want to freeze the ones that are higher up here, basically the higher like level complex, patterns. And then you might even try to freeze the whole thing and see how well it does, and then unfreeze more of the higher features and retrain on top of those. And that way you can build up new contextual information versus keeping, what's it called? Keeping just the, like you want to keep the really low level features and then retrain the high level features. So that way you can get a better classification. Okay. Cool. Any other questions? All right, so I'll go ahead and stop it here then.